Hi everyone. In this section we're going to finish up chapter 12, and this is going to be on graphing special families of surfaces known as quadric surfaces. And we're going to use some of our techniques that we developed in chapter 14, this idea of traces. If you're watching this and you haven't done the chapter 14 material yet, that's alright. I'll introduce the idea of a trace in this section as well. So here's the idea. We've got an equation. In this case it's x plus 2y plus 3z equals 4. And we'd like to figure out what the collection of all points with coordinates x, y, z that satisfy this equation, what that looks like in three-dimensional space. So what kind of object is the graph of this equation? So the way we can do that is we can use this idea known as traces. And what traces essentially allows us to do is to convert this problem in 3 dimensions to a bunch of problems in 2 dimensions. So let's see how we would do this in particular. We would look at, let's say, the trace. Well, I'll color code these here. We'll look at the trace in the xz plane. So what this means is instead of trying to find all points in 3-dimensional space with coordinates x, y, and z that satisfy this equation, I'm just going to look at how this surface intersects the xz plane. So I'm going to be interested in what does it look like when y is equal to 0. So I take my equation and I substitute y equals 0 into it, and I get x plus 3z is equal to 4. And from this, I realize, hey, this is a line in the xz plane. So this big surface, I'm trying to get a feel for what it looks like. It intersects the xz plane in a line. And we can try that again. We can say, well, how does it intersect some of the other coordinate planes? So what is the trace in the yz plane? Well, in the yz plane, that's when x is equal to 0. So when I substitute x equals 0 into the equation, I get this equation here. And again, this is a line. This is a line in the yz plane. And we can continue doing this. Do it for the last coordinate plane. So what is the trace in the xy plane? This is when z is equal to 0, and that means our x and y values must satisfy x plus 2y is equal to 4, which is again a line, in this case, in the xy plane. Okay, so we get various lines. And then I can use this information to start to get a sketch of what this object looks like. So I'll draw my coordinate axes in. This is our x-axis, our y-axis, and our z-axis. And what we found is that in the xz plane, it's given by this line. Now I only need 2 points to determine a line, so what I can do is just ask myself, where does it hit the z-axis? So when it hits the z-axis, that's when x is 0, so that means z is equal to 4/3. So it hits it up here at a value of 4/3. Where does it hit the x-axis? That's when z is 0, and so that's x is equal to 4. And so then we can connect those two by a straight line, and I can then continue this line because now I have those 2 points on it, and so the line in the xz plane looks like this. So that's where the graph of this original equation, when it intersects the xz plane, it looks like this line. And we can do that for the other planes as well. So what about the yz plane? Well, it intersects it in that line, and we can play the same game where I say, where does it intersect the z-axis? That's when y is equal to 0, so we already have that it intersects at that point there. Z is 4/3, and x and y are both 0. Where is it intersecting the y-axis? That's when z is 0. So again, I'm looking at this equation. When z is 0, y is 2. So I know it has to pass through this point here, and it's got to therefore intersect along this line. So there's our line segment, and then we can just continue our line. And this line lives in the YZ plane. And then lastly, for the blue line, well, we already have the 2 points it passes through. It's going to be these 2 points here, and we can connect those up by a line segment, and then therefore by a line that lives in the, I'm going to fix that bottom part because it's supposed to be crossing at that axis, or at that point. So there it's crossing. So there's our line in the YZ plane. And so those are the 3 lines where our surface intersects the axes. Intersects the coordinate planes, also where it intersects the axes, but it intersects them at those points. And now we can go ahead and get a feel for what this is. So it's going to be made up of all of these. Maybe I'll just draw some line segments. So it's going to be made up of this triangle here, and then extended. So it's basically this whole plane. I'll draw some more line segments outside. So it's basically a plane that looks like this, where it intersects those coordinate planes in these 3 line segments. So this is going to be a plane. And we already knew this. I mean, the section prior was about lines and planes in 3 dimensions. So we already knew an equation like this was going to be a plane. In fact, we knew that it was going to be a plane with a normal vector of 1, 2, 3, and points. We could figure out what points live on that plane. The points would be, take any 2 of the x, y, and z values to be 0 and find the third one. So that would be 4, 0, 0. That would be when x and z are both 0, y is equal to 2. And when x and y are both 0, z is equal to 4/3. So we already knew that bit of information, that it was a plane, normal vector passed through these 3 points. But this was to illustrate that we could also do this technique of figuring out how it intersects the coordinate planes and get that, that idea that it's actually a plane as well from that. So and this is going to be the idea that we're going to be using moving forward in this section. We're going to figure out how it intersects coordinate planes and also planes that are parallel to the coordinate planes. And these are these ideas of traces. So let's get a feel for the next one. So we're going to want to sketch the graph of z equals x squared plus y squared. So how are we going to do this? Well, I'll sketch maybe the coordinate axes over here. So there's our coordinate axes, x, y, and z. And we're going to use the same technique of finding traces. So we'll take the trace in the, and I'd like to do in the x, y plane at first, but if I took how it intersects the x, y plane, that's when z is 0, z would be 0, so that means x squared plus y squared is 0. The sum of 2 non-negative numbers, if they're going to be 0, each of them has to be 0 itself, and so that would just give us a point. So maybe I'll draw that point in, but say we're really not getting much information. So what I'll do instead of saying take the trace in the x, y plane, I'll say let's take a trace in a plane that's parallel to the x, y plane. So we'll take a trace in the plane z is equal to some k, where k is a positive value. It could be equal, maybe greater than or equal to 0, because we've already done the 0 case. It's just that single point. So what does this look like? Well, that says consider a constant value for z, let's call it k, and let's figure out what this looks like in the z equals k plane. So again, we're taking this plane, I'll draw it in here temporarily, but I'm going to erase the plane soon enough. So we're taking a plane at a height k, and we're saying, how does the surface intersect that? So it's going to intersect it in a curve, and we've got the curve now. It intersects it in a curve that looks like this, x squared plus y squared equals a constant. And so that's a circle. It's a circle of radius root k. So this is a circle. Its radius root k. And so that says for various values of k, the higher we go up the z-axis, our surface is intersecting it at circles with radius root k. So I'm going to get rid of the plane here, because this is going to be sort of inherent in our discussion that we're at any level we are thinking about how it intersects the plane. But the idea is we're getting now circles. So we're getting a circle, like right up here, and then a little bit lower we're getting another circle, and then so on. A little bit lower we're getting another circle. And so these are going to be how this surface is going to intersect these horizontal planes. So we can think of these as the slices of our surface. Okay, what about the trace in one of the other planes? So the xz plane or the zy plane. So we could do, again, much like we've done with this first one, is say we're not interested in exactly how it intersects the plane, but how it intersects planes that are parallel to that coordinate plane. But for here, with these next ones, we'll just stick with the xz plane and the yz plane itself. So trace in the xz plane. What would that be? Well, the trace in the xz plane, that's when y is equal to 0. So we would plug that in, and we get that z is equal to x squared. It's like, okay, when it intersects the xz plane, it looks like a parabola. So maybe I'll draw my parabola something like this. So it's sort of coming down, intersecting, and then going in the other direction like that. So this is in the xz plane, so I'm kind of drawing it with perspective, like we're looking at it. It's got to be a parabola when you stare at it in that direction, in the xz plane, but we're sort of looking at it on an angle. Okay, what about the trace in the yz plane? Well, that's when x is equal to 0, and so z is equal to y squared. So it's a parabola. That is, now I've got to make sure I can connect these things up. So it's a parabola. I might have to adjust some of my circles so that they come out and meet it. It's a parabola that looks like that. And I'll thicken my circles just a little bit so they come out and meet these parabolas. So there's our circles. And the top and bottom, or the top and the point at the bottom were fine. So there we go. And that blue curve is our parabola in the yz plane. And now, with these couple of parabolas and a few circles sketched, we get a feel for what this object looks like. Looks like this sort of bowl kind of thing opening upwards. Or you might maybe want to think about it this way. It looks like that blue parabola rotated around, like a lathe, to rotate around and sort of make this bowl shape. And that's the object that we end up getting. And this object that we've created here, this is known as a paraboloid. It's the three-dimensional analog of a parabola. And the thing to keep in mind is that how was it built up in terms of the traces in the various directions? Well, there was a parabola when we looked at it and how it intersect one of the coordinate planes. There was another parabola and how it intersect the other coordinate plane. And then there was a circle. And that's how this surface was intersecting these planes parallel to the third coordinate plane, planes parallel to the xy plane. So this is, in some sense, this is dominated by parabolas. Of the three different directions we can sort of look at these traces, two of them were parabolas, and then the other one was a circle. So we could call this a circular paraboloid. The dominant feature is the parabolas. It makes up two of those directions, but the other direction was sort of made up by these circles. The traces were these circles. So we could call this a circular paraboloid, as opposed to an elliptic paraboloid, which we could get by maybe throwing some various values in here. Like if I threw a 9 in front of the y, then the cross sections or the traces in the z direction would no longer be surfaces. They'd no longer be circles. They'd be ellipses. So we would call that an elliptic paraboloid. The other two directions would still be parabolas. One would be z equals x squared. The other would z equals 9y squared. Both are still parabolas. They're slightly different shapes than each other. So that's, I'm going to erase the 9 now, but that's circles coming, or the circular part is coming from that third direction, what the shape is. And so you can start to see that there's a little bit to naming these things, and we're going to start to explore these names a little bit further. Okay. So that was an example of a plane and a paraboloid. One of the general shapes that's always worth knowing how to do, or worth knowing how to sketch, and also knowing what the definition is of it, is a cylinder. So this doesn't look like your cylinders from the past probably, but this is the most general definition of a cylinder. So what is a cylinder? A cylinder is a surface that consists of lines called rulings, and those are the orange lines in our diagram here, that are all parallel to a given line. So let's just identify. So here's a line. I'll draw this bottom one down here. There's a line. All of the other orange lines are parallel to it. And all of the orange lines as a whole, they pass through a given plane curve, namely this green curve along here, or greeny bluey kind of curve along there. And so this is what's known as a cylinder. Typically, you're used to thinking of that green curve as being a circle. So I'm drawing it with a little bit of perspective. It's a circle that's going into the page. And so if that green curve is a circle, and we take all of the lines that are, let's say, parallel to this line, then what we end up getting is your classic cylinder that you're used to from probably high school. Maybe I'll draw it like this, and then I'll put in some dotted lines back here, a little bit more perspective, maybe a couple of dotted lines here to say those are going on in the back. And so this is your classic cylinder that you're probably used to seeing. This one is what we call a circular cylinder, because the cross sections in this one direction, namely the vertical direction, they are circles. The cross sections in the other directions are straight lines. So this is our circular cylinder. In fact, this is one of many kinds of circular cylinders. So for example, we could get the same picture. I'll draw that same circle. I'll dot the back circle just to indicate that's in the back. And if I start with a line that's on slightly an angle, so it's not at a perpendicular angle or not at a right angle to the circle itself, and then I take all of these lines parallel to it that pass through the circle, then what I get is a shape that looks like this. And again, maybe put some dotted lines in there to indicate the ones at the back, and so on across. So this is also a circular cylinder, because again, its cross sections are circles. As you move up, the cross sections are circles. The key difference, though, is that one of them has an angle that's not 90 degrees. So here's a 90-degree angle between our side and our plane that our circle lives in, and the other one doesn't have a 90-degree angle. So maybe I'll indicate this is not 90 degrees. And so in this case, the first one, we would call this a right circular cylinder. And so that's the definite name for this cylinder that you're used to just referring to as a cylinder, probably from previous math classes. but the precise name of this cylinder is it's a right circular cylinder. And that's to emphasize the fact that there are many kinds of cylinders out there. And a cylinder, as given in this definition, is precisely this. We've got a green curve, we've got a line that passes through that green curve, and then you take all lines parallel to that line that pass through the green curve, and that makes up a cylinder. Okay, so many varieties of cylinders that we can encounter. Now let's get some practice in sketching some graphs, and we're going to use the idea of traces to do that. So this next one is x squared plus y squared is equal to 4. So we want to find the set of all points x, y, z. Again, we're in 3 dimensions, so it's all points with coordinates x, y, and z that satisfy this equation. Let's maybe think about what is the trace in the z equals k plane. So you can think about it as the trace in the xy plane. That's when z is equal to 0. Or planes that are parallel to the xy plane, and that would be for various values of z, just a horizontal plane at that particular height. So we'll look at that in general. What is the trace in the z equals x plane? So in that plane, the z value is x, and what do our x and y values satisfy? Well, they satisfy this equation, and this is a circle of radius 2. So that means that in our coordinates x, y, z, what we've got is at any given height, we've got a circle of radius 2. So that's true no matter what height we're at, even for negative z values. Always a circle of radius 2. And so there is our corresponding graph. And it just continues on down and up. And what kind of graph is this? This is our right circular cylinder. Right circular cylinder. The right referring to the fact that there's a right angle between the side and the plane that the circle lives in. Circular because the cross sections are circle, and a cylinder because it satisfies the definition of a cylinder. Let's have a look at the next example. Y equals z squared. So y equals z squared. Let's look at the trace in the which direction? Well, much like the one up we did above, where we took the trace in the plane of the variable that's missing, essentially, we see that this consists of all points x, y, and z that satisfy this equation. X has no conditions on it, no restrictions on it. So if we look at the trace in the x equals k plane, then that's the corresponding relationship between the x and y values, sorry, the z and y values, which means it's a parabola. So the traces in the planes x equals k are parabolas. And so we'll try to get a sketch of this. So there's our x direction. We've got y and z. So the first parabola I'm going to draw is the one in the yz plane. So that's going to be y is equal to z squared. So it's going to kind of look like this. It's going to be a parabola that's opening up like this. I'm just going to try to maybe get it so that we can carry it on. Maybe I'll draw it like this. I'll make this bottom a little bit longer. I'm only going to draw a portion of the surface, so I'm going to try to set myself up for success in drawing this. So there's our parabola. Right? It would go on forever, but this is a parabola in the yz plane. But now, as I move out along the x-axis or into the page along the x-axis, this surface that we're trying to sketch is going to intersect the planes in this same shaped curve. So what we can do is we can just draw that curve again. So I'll draw it a couple of times. It's going to look like I'm going to try to draw the same curve. Maybe the best way to do this is to just cut and paste, just so you see that I'm trying to draw the same curve here. So I will try to draw it in one sweep. And then let's see if I can just grab the tip of that and say copy, paste. Yes, I got it. Good. So, and then we'll copy and paste again. Copy, paste. And so what I'm doing is I'm taking these curves and I'm just sort of dropping them along at various different points along the x-axis. Because the idea is no matter how I'm slicing my surface in a plane x equals k, it always is going to give me a parabola. And so now I can connect these things up. So our parabola are going to join together. They'll go off in the distance like that. And maybe I'll grab one more copy and slide it in back here. Something like that. And so there is our surface. It's basically this, what I guess potentially looks like a feeding trough, maybe turned on its side, like something farm animals would eat out of, like a trough that's sort of turned on its side. That's our resulting shape. So this is a cylinder. Right? This is a cylinder. Why is it a cylinder? Because along the x direction, all the cross sections look identical. They're all parabolas. And so that one parabola is sort of our base curve, and then we take all lines parallel to the x-axis and we let it pass through that base parabola curve, and that generates this cylinder. So this is a cylinder, and we could call it a parabolic cylinder, because instead of being made up of circles like the one above, these are made up of parabolas. So this is a parabolic cylinder. All right. Just so you know, if you are having some troubles visualizing these kinds of things, go to math3d.org and we can go ahead and say we'd like to sketch. Let's say we want to sketch that last surface, y equals z squared. So if I'm using an explicit surface, I can't use that one because this is a z, inherently it's a z equal to whatever expression of x and y I want. So I'm going to get rid of that. What I'd like to use is an implicit surface, and that gives me an equation. And so then I could put z on one side, I could put z on one side, I want the y on this side, and I want z squared on that side. And there is the object that we just drew. It's basically parabolas opening along the y-axis in the yz plane, and then all traces of those essentially in all of the x equals k planes. So it's basically the parabola sort of shifted out front and out back along the x-axis. And so that's ultimately the kind of surface that this equation describes. All right, let's have a look at the most general kind of surface that we have in this particular section. This is known as a quadric surface. So a quadric surface are basically some of the things we've seen already. They're equations where the highest power that appears on one of the variables, or both together in some sense, is a square. So for example, let's scroll back. We've got a y equals z squared, or an x squared plus y squared equals 4. We keep going back up here. Z equals x squared plus y squared. So in all of these cases, the highest power we have was essentially a square. So in general, a quadric surface is the graph of a second degree equation in 3 variables, x, y, and z, where the highest power is a 2. So we can have an x squared, a y squared, a z squared, or a product of x and y, product of x and z, and so on. And there could be some lower powers as well. This is the most general form of such an equation, but we can always use transformations to put it into one of these two forms. So we can either put it in a form like this or a form like this, where either all the variables are squared or two of the variables, in this case, are squared and one of them is not. So these are our two standard forms. We could have less. For example, there's nothing here that says that a has to be non-zero. So a could be 0, in which case we could have a y squared, a z to a single power, and then no x squared appearing. That's fine. So you just notice that the a, b's, and c's, any of them could be 0 in this case as well. So these are the kinds of equations that we are going to look at right now, and we're going to try to classify all of the kinds of surfaces they can represent. So let's get an idea for this one where we've got all of the variables squared. So x squared plus y squared plus z squared equals 4. What kind of surface is this? So let's look at the trace in the z equals k plane. What does this look like? So z equals k, that means z can be substituted for this constant k. So I can write it as x squared plus y squared is equal to 4 minus k squared. And the idea with this is that that's a circle. We need to make sure that z is trapped between -2 and 2, because if z was bigger than 2 in magnitude, let's say z was 5, for example, then the right-hand side would be 4 minus 25, which would be a negative number, and x squared plus y squared could never be a negative number, so there'd be no solutions for x and y. So in order for there to actually be solutions for x and y, we need z to live between -2 and 2. So what that means is that when we draw a horizontal plane to cut this surface, it has to cut it in a circle. And the circle, its radius is biggest, so what is the radius? Maybe I'll write that down. The radius is the square root of 4 minus k squared. So that's going to be biggest when k is 0, because when k is anything but 0, we're going to get 4 minus something, which makes that value smaller. So when k is 0, we get the biggest possible radius for our circle, so I'll draw one of those circles in here. It's going to look something like this. Then as I move up the z-axis, or even down the z-axis for negative k values, what we get are smaller and smaller circles until we hit a k value of 2, in which case we get a circle of radius 0. So I'm going to draw some lines of or curves of reference here so that now I can draw these circles in. So we get these circles that go up, and they're shrinking in radius as we go up. And similarly, as we go down, we'll get these circles as well, like that. And so what we end up getting, maybe I'll fix that middle circle so that it looks like it's consistent with the other ones. I might have drawn it a little bit too wide, so something like this. So those are circles shrinking as we go up towards z equals 2, shrinking as we go down to z equals -2. So that's z equals 2. This one is, I want it gray there. This is z equals -2. This is, of course, y equals 2 and x equals 2. And now with these traces, what we can see is, hey, that looks an awful lot like a sphere, and sure enough it is. This is a sphere. And we already knew that equations like this are really coming from the distance formula, and they do represent spheres. So this is another way to think about why this equation is a sphere. But moreover, it says that in this family of quadric surfaces, spheres are a part of this family. So that was our first example. A sphere is what's known as a quadric surface. What else can we get? Well, let's look at this next one. Y is equal to x squared plus z squared. We'll get our sketch again. X, y, z. We'll build up some information. So we'll say, what is the trace in the y equals k plane? So y equals k plane. That's a plane that's sort of cutting like this. I'll briefly sketch it in. So that's y equals k. How is the surface intersecting this plane? That's what we want to know. So I guess I'll just get rid of that plane so it doesn't clutter up the diagram. But what is our intersection going to look like? Well, that's when k is equal to x squared plus z squared. Oh, and that's a circle of radius root k. So we know they're going to be circles. As we move along the y-axis, we're getting circles that are getting bigger and bigger and bigger. So for example, they'll look something like this. We'll get a circle here, and then a little while later we'll get another circle which is a bit bigger, and so on as we move down the y-axis. What else do we get? Let's look at our trace in the, we'll do the YZ plane. So this is the plane when x is equal to 0. So the YZ plane, what does it look like? Well, when x is equal to 0, we get a y is equal to z squared. That's a parabola. So that's going to look like this when we're looking at the YZ plane. So that's sort of the, I'm ignoring the z or the x-axis that's coming out, and I'm just going to draw a parabola. So it looks like this. There's our parabola. There it is there. Make sure it's nice and smooth as we come in. Make sure my circle actually comes out and touches it. And so there we go. We got our parabola. And lastly, we could say what's the trace in the xy plane. That's when z is equal to 0. And that's going to be a y is equal to x squared. So again, that's a parabola. So maybe I'll draw that in a slightly different color. It's going to look like this. It's a parabola in the xy plane. So for this object, what we have is, I'll put these in a different color. We've got circles in one direction. We've got a parabola and a parabola. So there's two directions where it looks like parabolas, one where it looks like a circle. And so this is a circular, which I'll put in brackets because we typically we don't refer to it as such. We just refer to it by its last name, paraboloid. So this is a circular paraboloid. Okay, let's have a look at the next one. So x squared over 4 plus y squared over 9 plus z squared over 16. What is this going to look like? We can do the traces in the z equals k plane. That's going to be x squared over 4 plus y squared over 9 is equal to 1 minus k squared over 16. I'll put that in parentheses just because it's just some constant on the other side for a given value of k. Z's got to live between -4 and 4 in order for that right-hand side to be a non-negative number, and so that for us to actually have values for x and y that satisfy the equation. But what are these objects? So in this z equals x plane, this is x squared over 4 plus y squared over 9 is equal to a constant. These are ellipses. So this is an ellipse for various values of k. And as k gets bigger, the ellipses shrink in size. So what we end up with is ellipses as we move up and down the z-axis that are getting their biggest at z equals 0, and they get smaller as we move up. When z is equal to 0, or in other words, when the trace is for the value k equals 0, we get the points 2 and -2. Extend that a little bit. 2 and -2 are a couple of points on the x-axis that it touches, and -3 and 3 are a couple of points on the y-axis it touches. There's got to be an ellipse that passes through these. This is the biggest ellipse that we get of all the all the traces or cross sections. So there's our ellipse, sort of drawn with a bit of perspective going off into the page. And then as we go up and down, these ellipses get smaller, and the maximum height that we get is going to be up here at a value of 4 and a value of -4. And so I'll just connect these things up as well by some curves here. And so it's going to look like this. And so that's our shape. We get ellipses as we go up. So maybe I'll draw one of these trace ellipses in. It comes here, and then it sort of goes like that. So that's an ellipse at a particular height. And we've got that big ellipse in the middle there. As we go up and down, we get these ellipses, and this is known as an ellipsoid. In all different directions, the traces in the xy plane, the xz plane, the yz plane, they're all going to be ellipses. So this is an ellipsoid. It's just a generalization of the sphere in some sense, where we've got stretching happening. How about another one? Y is equal to x squared minus z squared. So let's look at listing it by its traces. So we got a trace in the x equals k plane. We will look at a trace in the y equals k plane, and a trace in the z equals k plane. So how is it looking in the three different directions? When x is equal to k, we get a y is equal to k squared minus z squared. Think about what kind of shape that is. This is in a plane that's parallel to the yz plane. So what kind of shape is this? Well, it's a y is equal to a square in z, so this is a parabola. And then we've got a k is equal to x squared minus z squared. So this is a curve of the form x squared minus z squared equals a constant. This is a hyperbola. And then what about the last direction? Z is equal to k, so that's y is equal to x squared minus k squared. That's a parabola as well. So we have two directions where the traces are parabolas, and one direction where it's a hyperbola. So if you think about our naming, I've sort of hinted at our naming convention. The dominant one is like the last name, so it's paraboloid. What kind of paraboloid is it? It's a hyperbolic one. So this tells us that it's going to be what's known as a hyperbolic, or what we call a hyperbolic paraboloid. What does it look like? Well, I'm going to draw it first and then put the axes in after, and then we'll do a little sketch in math3d.org just to get a visual for this. So a hyperbolic paraboloid, it's best referred to as a saddle. It's like a saddle that you would put on a horse's back to ride. So what does a saddle look like in terms of a sketch? Well, it would look something like this. So there's a saddle. So the idea is, if I add a little bit more of a diagram here, we got the person, their legs hang down on either side, and then their hand grabs the reins or whatever, and so that's what's sitting in front of you and behind you. So it curves up in front and behind you, but then it drops to the sides. So I'll remove the person from our saddle picture. But the idea is it's falling away. In one direction, the surface is falling away, but in the other direction, it's going up and down. Or sorry, it's going up in both directions. So it goes down in one direction, goes up in the other direction. And this is what's known as a hyperbolic paraboloid. In this particular case, our axes are going to look like this. So we've got one that's going to be vertical here, and then one that's opening in the down direction. And we can maybe think about what directions. Probably should have put these in a different color just to avoid the confusion with the actual sketch of the surface in the background. So there's our coordinate axes. Might be able to think about, from the parabolas that we have. Well, we've got a y is equal to k squared minus z squared. So that's a parabola opening down because of the minus z squared. So in which direction do we have a parabola opening down? Well, if I look at my diagram, I see that there's a parabola opening down, and I can sort of see it as it's going along the curve. It's opening down and so on along this direction. So along this direction here, it's opening down. So that means that must be our, so this is our y is equal to k squared minus z squared. So that was in our trace in the x equals k plane. So those must be the traces, those purple curves I just drew on, must be traces in the x equals k plane. So this must be the x direction. Okay, so this is going to be our x direction. Now, which is the positive and which is the negative, we still have to decide that. So let's just label that one x for now and see what happens. Then we got another direction that we have a parabola. In this case, the parabola is opening up. So I can see an opening up parabola right here. And then as we move along in this direction, so as we move along in this direction, we see that we still have parabolas that are opening up. They're just dropping. So they're parabolas that are opening up, but they're dropping. So that's given by this expression here. Y equals x squared. That's a parabola opening up, but it's dropping because of the negative k squared. So that means that this direction must be z. So this is our z direction. And now if that's supposed to be our z direction, and we've got our two other, and this is going to be our y direction, of course, because it's the last direction, then I need x cross y to give me z. So that's why I've labeled the x over here, the y, positive y-axis going up, and the positive z-axis coming out of the page. So let's get a feel for this one a little bit more. So I am going to go ahead and bring up a graph of this equation, y equals x squared minus z squared. See the x-axis coming out of the page here, the y-axis off to the right, the z-axis going up. And what we've done is we've done these various traces. So what's the trace in the x equals k plane? So what our trace is we're going the x, so I'll turn on our x direction. So I've drawn a plane, and we're allowed to now let that plane go through various x values given by k. So I'm letting this plane just sort of sweep over the surface. The intersection between them is given by this yellow curve. And if I look at that yellow curve as I let it sweep along, that yellow curve that's the parabola. That's the parabola we're getting. So a parabola in one of the directions. Now let's take a different slice. So now I will slice it in the y direction. So there's our y direction slice. And we just let that plane sweep over various different y values and see how it intersects. And these are the hyperbolas that we're getting. And so as we drag our curve along, we get these different hyperbolas. So now these ones are opening sideways. So those are the hyperbolas in the y traces. And then lastly, we can go to the traces in the z direction, or the traces in planes that are parallel to the xy plane, so for various z equals k values. And those are parabolas as well. We can see those parabolas in the diagram here. So there's our intersections and parabolas. So we've got two directions with parabolas, one direction with hyperbolas, and so this is known as a hyperbolic paraboloid. All right. And now our last example, an equation of the form x squared plus y squared minus z squared equals 1. So you look at this and you might say, oh, that kind of looks like a sphere, except there's a negative value in front of, or a negative sign in front of the z squared. So let's see how that affects the shape. So we're going to get our traces, x equals k. So that's going to be y squared minus z squared is equal to 1 minus k squared. These are hyperbolas. We got y equals k. It's almost very similar to the x. In this case, it would be an x squared minus z squared equals 1 minus k squared. This is a hyperbola again. So it's a two hyperbolas so far. So we can already maybe think that the name of this surface is probably going to be called a hyperboloid. And then what about z equals k? So that's x squared plus y squared is equal to 1 plus k squared. And those are circles. So this is going to be what's known as a hyperboloid. And is there any restriction that k has to have? When I look at this circle equation, if I think back, if I scroll back up here to the ellipse one, maybe I'll even go back further and go back to the sphere. When I go back to the sphere, we had an x squared plus y squared equals 4 minus k squared. And we looked at this and we said, hey, wait a minute. If that's negative, we're not going to get any solutions. So that gave us these restrictions on z. Z had to be between -2 and 2. Otherwise, we weren't going to get any solutions. And that meant that our sphere couldn't occupy or couldn't consist of points that had z values bigger than 2 in magnitude. So if I scroll down to this one, and I look at my equation for my circle, I see that k can still be anything because it's 1 plus k squared. That's always bigger than or equal to 1, and so there'll always be solutions. And so what we call this is a hyperboloid of one sheet. Okay, you might say, well, that seems weird. And I'll say why we call it that in just a second after we get a sketch of this. So we got our x direction, our y direction, our z direction. I'm going to focus more on the circles than the hyperbolas in getting this sketch. So this says when k is 0, when the z value is 0, it's a circle of radius 1. So we're going to have a circle here of radius 1. Maybe I'll dot the back side of the circle. So there we go, there's our circle. And as our z value changes, as our z value increases, our radius of our circle is going to increase. Because it's x squared plus y squared equals 1 plus k squared. The radius would be the square root of 1 plus k squared. So as k gets bigger, the radius gets bigger. So our radius is getting bigger and bigger and bigger, so I'm going to sort of indicate that by as I go up the z direction or down in the z direction, I get circles that have bigger and bigger radiuses, or radii. And so this is our hyperboloid. Hyperboloid. And we call it of one sheet because you can make this thing probably out of one sheet of paper. You can get from any point on the surface to any other point on the surface without leaving the surface. This is in contrast to a hyperboloid of two sheets, which I'll show you in this list of these kinds of shapes. So this is a hyperboloid of two sheets. And you can see there's a very subtle difference. The hyperboloid of one sheet just had one negative sign in it, and then there was a 1 on the right hand side of the equation, where the hyperboloid of two sheets has two negative signs in it, whereas we've got 1 on the other side of the equation. So these are both known as hyperboloids. They both consist of hyperbolas in two directions and ellipses or circles in the other direction. It's just that for the second one, there can be some values of k for which you don't get solutions for that circle equation. And so you've got a gap in the middle. But this is our collection of graphs of quadric surfaces. So we've got our ellipsoid up in the top. That's basically our sphere as well. We have our paraboloid, which we've seen over here. We've got our hyperbolic paraboloid. So there's the elliptic paraboloid and the hyperbolic paraboloid that we've seen. We've got a cone. We didn't talk about this one, but there's the equation right there. It's got the 0 on the right-hand side of the expression. So it kind of looks like the equation for the hyperboloid of one sheet, except there's a 0 instead of a 1 on the right-hand side. And then we've got our hyperboloids, one sheet and two sheets. And so this is our collection of shapes of quadric surfaces. And so you have a look at this table, make sure you kind of see the difference between them in terms of their equations. How do you remember which one is which? Through traces. And that's why I've listed in all of these cases, the traces. So this one has two hyperbolas and one ellipse. This one's two hyperbolas and one ellipse. So they are both hyperboloids. How do you tell them apart? You've got to look at the ellipses themselves as to when they are defined. And similarly for the other ones. All right, so that's it for this section. Thanks very much for watching, and we'll see you next time.